Damn it, Steve. If you're going to solder leads on these LEDs, you need to use a real soldering iron like this one. Not that silly little thing that you're using. My friend Steve called me this morning, whining that he was having trouble getting leads soldered on these Rebel LEDs. These are Luxon Rebels. These things will handle 700 milliamperes. They are incredibly bright. That's about 2.5 watts plus on the white ones. And if you take a look at this picture, those are standard 1/4-inch squares on graph paper, and that's a small paper clip, not the large Jahumbas ones. That's the small, standard, tiny little paper clip that you get. Gives you an idea of how big these are. And over here, on this guy right here, let me get something better to point. Where'd my pencil go? There it is. This guy right here, the big pad you see is a heatsink pad. That's designed to be bonded or soldered to a heatsink. And the two small pads are the contact pads. Now normally when I use these, I solder to the front surface, which is the two little connections right here, but there's a trick to that. And we'll get to that here shortly. Free air, you can run these at about 100 milliamperes, which is about 0.6 of a watt. They get a little warm, but they're well within the safe limits for the junction. To go any higher than 100 milliamperes, you have to heat sink them. Now, what I've done as an experiment is I took a piece of copper wire, house wire, and merely soldered it right to the pad on the back. Now, this also has the advantage of giving you a stand, hold it steady while you solder the leads on. But running it like this, I should be able to run this thing up close to a watt with no problem. And plus it gives you a couple of places to mount it with screws. You could put a whole string of them on there if you wanted to, but then you'd have to derate it because you wouldn't be able to get rid of all the heat. But he was looking for an application to replace a lamp and a piece of scientific equipment he had, and this would probably fit the bill quite nicely. We'll show you what these things can do here. You know, if Steve had only manned up this morning and used that soldering iron that you saw in the intro, he wouldn't have had any trouble at all. But we'll show you how to do it with a regular iron, because I know you guys can solder. We have one of the white LEDs mounted here. Now I'm going to start turning up the current on this, and I'm going to start at about 50 milliamperes. That's 50 milliamperes, and that's pretty doggone bright. I mean, that hurts to look at it. I don't know how it looks in the camera here, but by golly, that thing is bright. Now I'm going to bring it up to 100. There we have it. There's 100 milliamperes. And I got spots in my eyes just from playing with these. This is a double-sided one that I made. And this is kind of a useful little beast. Actually, the double-sided one I shouldn't run that hot because there's two of them pumping heat out. So there's back to 50 milliamperes. And these are great. You can stuff this thing, because it's double-sided, you can stuff this thing down the spark plug hole of an engine and inspect the top of the piston. Or let's see if we can do this. You could stuff it down the bore of your shotgun. See how nicely that lights up the bore of that piece of pipe? You could inspect the bore on your rifle. You could inspect plumbing. You could stuff this thing in a cavity in a wall. If you're trying to fish wires through, it'll give you some light down there to see what's going on. But it certainly is nice for inspecting the bore of a shotgun or a rifle. And if I turn the power off on this one, and we'll see how close we can get this to focus. I don't know if we'll be able to get this camera to focus. Maybe if I put something up here with it. There you go. There's two of them back to back. All I did is put some double-sided tape between them, put a little jumper on one side and put the wires on the other, and there you have it. You got a bore light. Let's try some of the other ones. Right, we have this stuffed in a glass of water. I'm using distilled water because I have it down here in the lab, but at these voltages, I don't suppose it would matter much. Right now we're looking at 2.8 volts across the LED at 100 milliamperes. So let's do the maths on that. We got 2.8 times 0.1. So you're looking at 0.28 watts, a little bit over a quarter of a watt right now. And while I'm on the subject here, we'll take a look at these two slides. Here's where you can get the white ones on eBay. Now, I'm sure there's other vendors, but this is a fairly good price for these LEDs. They're somewhat pricey. And I have no affiliation with these vendors. I just went online, and the first ones I found with reasonable prices, selling the Luxon Rebels, I threw it up. This one here is the red, and you can buy these still in the pocketed tape. And I'm kind of wondering if actually my firm put these in the pocketed tape. It's what we did years ago. We sold the equipment to put these into pocket tape. And in fact, this is one of our LED boards using these Luxon LEDs. These were used for the cameras on the vision system of the machine that picked the die and placed them in the pocket tape. These are the same 700 milliampere, but these are the red. These are the Luxons. We actually used to hit these with 6 amperes of current. That's right, 6 amperes, not 600 milliamperes, 6 amperes, but we only did it for a millisecond at a time. So the duty cycle was very low. On our fastest machines, the duty cycle would have been a little bit under 200 milliseconds per cycle, which means with 1 millisecond on, that's a 1 in 200 duty cycle. So we were able to run them without a heat sink. There is some copper on the board behind there mounting for the mounting pad, but it doesn't amount to a heat sink. With 1 millisecond exposure times, you didn't need anything. So that's 100 milliamperes. Let's crank it up. There's 2, 3, 4, 5, 6. There is 700 milliamperes. And if you don't think that's bright, let me tell you, I'm going to turn the lights out here in the lab in just a second. But just to show you, there's 700 milliamperes, and that's 3.261 volts across the LED. I'm measuring directly across the LED here. Let's call it 3.3 times 0.7. That's 2.31 watts. Now, with it in the water, with it in the distilled water, it's staying well within a safe junction temperature. What's interesting is if you stick your finger in here and stick it on the back of the LED, just for a second, it's cold because the water's circulating. But if you attempt to keep your finger there, holy bejesus, it doesn't take long to burn you. So you definitely have to have a heat sink at these current levels. Let's turn the lights out in the lab here and see what it looks like. I'm going to turn out that. Unfortunately, the sun is still streaming through the windows. But with the light out here in the lab, if we turn this thing around and aim it at the equipment, you can see that thing's throwing an awful lot of light. Pretty much all of this is in shadow in this part of the lab, and you can see we're tossing out a fair amount of light with that LED. One LED. Let's turn the lights back on here briefly, or at least one of them. I'm going to turn this off. I'm going to put a red one in here instead. The red ones, to my eye, look brighter. And in setting this up, I've been doing this for a few minutes. These will hurt your eyes. I'm walking around, I'm seeing spots right now. I'm having trouble seeing the alligator clips. It's probably doing damage, so I'm going to start to limit my exposure to this and look away. Here we have a red LED, and I'll just put it up to 100 milliamperes without the heat sink. And boy, oh boy, oh boy, I'll tell you what. It doesn't look that bright in the camera, but to the eye, holy cow, the camera's probably automatically limiting the exposure some. Let's put this one in the heat sink. Come on, grab the wire. There we go. And let's start cranking the current up on this puppy. It's getting brighter and brighter and brighter and brighter. There's 700 milliamperes. Now I'm not going to push it back there. I have pushed these to an amp, but I've broken a couple of them. They started sputtering at that point, and then after that they just sputtered all the way down to a lower voltage. And again, I'm going to turn out the lights. And I'll swing this around and point it at the equipment in the background. And I'll shield this so we're not flooding the camera. Take a look at that. That's some bright LED. And bear in mind, that's a single LED. In fact, let's leave it up there a minute, and I'm going to reduce the current down to 100 milliamperes, which is what you can run them in free air. And that's still lighting up that whole shelf. So these are very, very effective LEDs. And you know what? I just had a thought. I'm going to try something. I just went upstairs and got a piece of cut crystal glassware and stuck one of the LEDs in there. Eat your heart out, Big Clive. I'm coming for you, laddie. If you haven't been to Big Clive's site, do yourself a favor. If you like LEDs and you enjoy, LED products, finding out what's out there in the market, seeing stuff torn down, LED power supplies, yada yada yada, anything LED lighting, Big Clive does some awesome stuff. So drop over and visit his, I guess it's his page or his blog. It's just Big Clive. Do a search for that and it'll pop up. And this guy is just a prolific YouTuber, and he has all kinds of interesting videos out there. Fantastic stuff. And probably one of the best manual dexterity I've ever seen. I shake too much to do the stuff he does anymore. Let's turn the lights out and see how that looks. I'm kind of interested to see that with the lights out. Turn that out, turn that out, turn that out. Now that's 100 milliamperes. That'd make a hell of a mood light. And if we turn that up to 700, whew, that's too bright, actually. That's filling the room with light. You wouldn't want to use that for a night light. Let's turn it up a little more. Yeah, let's get brave. Keep going. There, whoop. There's about our brightest, right about 700 milliamperes. It's interesting. Once you get past the 700 milliamperes, it starts to dim again. I'm not sure what that phenomenon is, or as Big Clive would say, I'm not 100% sure. And I agree with him. I wouldn't know. But that's kind of interesting. Clive, you're welcome to steal that idea. He makes all kinds of lighting, by the way. He makes decorative lighting. He does some interesting stuff. Right, now, as I mentioned in the beginning of this video, the back side of this piece, and I don't know if we can get the light to reflect on it or not. Whoops, I had it there, not bad. There it is. And you can probably just make out the two pads down here. These are the normal contact pads that would be used when soldering this to a PC board, such as this illumination panel here. And this would get soldered to the heatsink. I find it more convenient when I'm working with these without a printed circuit board to solder to the top surface. Now if we take a look at this image here, you can see there's two contacts running down the front. One's kind of J-shaped on the right. That's your positive lead. And when you flip it over, the positive lead on the back is directly behind the positive lead on the front. In other words, instead of being on the right-hand side, your positive would be on the left when it's upside down. When it's right side up with the bubble or the lens facing you, the positive is the J-shaped one on the right-hand side. They use one of those flexible rubbery lenses on these. You can easily impress your fingernail into it, and that coating, it appears, is all over the top surface. Now whether that's by design to protect these against short circuit, which I imagine it may be, or whether it's just part of the molding process covers these, I don't know. They are designed to be put on a printed circuit board, so normally you don't connect here. These are pretty small pads. They look quite big in the photograph, but believe me, they're tiny. But since I put my wires on the top, I have to clean that off. Now let's see if I can get around the camera here and do this. It's much harder to do through the camera. I take a single edge razor blade and I just put it on the surface flat, and I just scrape towards me with the edge of the blade until I can see the pads getting shiny, and that way I know I've stripped off that coating. And I still don't think I have it on the right hand one. This is hard to do through the camera lens. Okay, you see what I'm doing. I'm going to move this away from the camera for just a moment so I can actually see what I'm doing. There, now the other side's clean and shiny. Oh, Get this over here in the camera and let's see if we can get that to reflect in one of the lights. Probably not. But at any rate, I have that rubberized coating off of those two pads right now. Normally, I don't have these mounted on a heatsink. I just set them right down on the table, and I'll just use my spool of solder to capture them in place. And the problem Steve was having this morning was every time he tried to solder these, of course, the surface tension on the solder, the thing would stick to the soldering iron and he couldn't get it off. So I told him, find something heavy and just pin it to the surface. Another alternative might be use an alligator clip, and that might even make it a little easier to work with, because now it's up proud of the surface of the table a little bit, and it probably would make it easier to manipulate your wire and get your wire down onto the pad. But we'll try this one, and this is going to be tricky trying to do this through the camera lens. This is a first for me. I'm going to put a little bit of flux on here, and the reason I'm doing that is I have some 031 solder here that's probably 10 years old, and the flux in here appears to have gone bad. If I try to use it without extra rosin, I get a very, very crusty looking joint. I do have heavier solder that I use, but I'm trying to use this stuff up. It's pretty gone, pretty well worn out, or shot, or whatever you want to call it. I've got some red-black 30 gauge wire. I've got a couple of spools of this. And while it's a good convenient size to work with on these, it's got some kind of PVC insulation that's extremely stiff. And I wish I'd made a different choice on wire when I bought this, because it's tough to do anything with these once they're soldered to it. The wire is, or the insulation is so stiff that it can be problematic trying to get it to lay flat. Let's see, I'm going to strip the other end of this. I can't do this in front of the camera. I'll bring the camera over here where I'm working, and we'll strip off the other end. What I should do is buy the cable for this camera that allows me to use a large monitor, and then I could probably see what the heck I was doing through it. But trying to see it through that little 2.5 inch screen on the back of the camera. This is a an old Canon Power Shot. I don't know what the heck's the model, SX20IS, that I bought years ago for traveling over in Thailand. It wasn't real expensive. I think I paid around $400 for it, and it was good enough. Gotta stop saying "and" so much. Somebody should send me an email about that and remind me, stop saying "and" so much. I think it's nerves. At any rate, I bought this for a trip to Thailand. I had an old Sony that had reached the end of its useful life, and bought this one. So I bought this one. No more "ands," Burn. No more "ands." So I bought this camera to replace it, and absolutely fell in love with it. It's a nice, or it was a super camera when I bought it. Only $400, not so expensive that if it got stolen or lost, I'd be brokenhearted too badly. But it did a good enough job. It took some excellent pictures. It takes HDMI video. I went to buy the AC adapter for this a couple of weeks ago so that I wouldn't keep running on batteries on this. I have rechargeable batteries that I use with it. However, after paying $400 for the camera several years ago, I find out that the stupid adapter is $100+. So I think I'm going to buy myself a simple the plug that fits into it, and build myself a battery pack that runs on D cells, or a 6-volt lead acid battery, or gel cell, or something of that ilk. So let's see if we can get down here, and I'm trying to keep my big fat fingers out of it. This is going to be hard to do. My hat's off to you, Clive. I don't know how you do it in the camera all the time. What I do is I've tinned up the wire, and I got my cheater headband on here. I'm going to tin up the pads, and if I can get in here, boy, this is tough behind the camera. Again, I'm not sure I'm going to be able to do this behind the camera. That one's tinned. That one's tinned. Okay. Whew, it It was a struggle, but we got her. So the two pads are tinned. And then I'm just going to take two wires here that I've pre-tinned. And where's my other solder? I am going to use the one with the good flux in it. It's a little heavier gauge, but this is difficult enough without using my crappy roll of solder. We'll pick up some fresh solder so we have a little fresh flux, and I'm just going to tack that down on that. There's one. I hope you can see what I'm doing. No, probably not from the looks of it. This is really difficult at this angle. I'm trying my best here. Let me try swinging it this way and see what we can do. I'm off to the side of the camera now. That wire's not lined up correctly, so we'll give that just a little bit of a tweak. I don't see my pliers, so I'll do it with the side cutters gently. That will line up better with the pad. I hope Clive's not watching this, because he's going to be laughing. He'll be saying, "I'm coming for you, laddie." And I can say stuff like that, Clive, because my family, or at least my mother's side, hails from Wales. I didn't mean that to come out like that. Anyway, the family on my mother's side is from Wales. So there you have it. There's the top surface soldering of those two wires. Now I'm going to hook that up to the power supply, and we'll put a thermocouple on here, and we'll see what kind of power we can safely run with that little heatsink. So let me get that set up. Right, it looks like we have everything in the shot. I first of all tried to use one of these normal thermocouples with a little ball in the end, but couldn't come up with any way to connect it to this copper piece. It wasn't going to take heroic efforts. And then initially I had reached for these alligator clips and figured I'd use those to clip it to this surface measuring thermocouple, and decided against that because that's an awful lot of thermal mass. So we came up with the two tie wraps, which are tying it to that little taut band, which is for taking surface temperature. Now the lab is pretty warm today. It's about 23, almost 24 degrees C in here, and I'm feeling it. In fact, I've gone around and shut all the heat off, but between all the equipment that's on in here and the heating plant that's running in the basement, we're getting on into spring and it's getting warm. Another month I'll have the air conditioners on down here. So let's start this out at 100 milliamperes. Now we know we can run this free air at 100 milliamps with no issues, but let's start there and see if there's any appreciable temperature rise. There we are at 100 milliamperes, and immediately we can see the temperature coming up even with that heatsink. I'm curious to see how good this piece of copper is. That's what this experiment's all about. And I should go and find out what the safe junction temperature is. Let me do that. Good God. The manufacturer says you can run the case temperature of this at 135 degrees centigrade. Ow. That is just ludicrously hot. I start getting nervous when something gets above 80 or 90 C. I remember reading in some trade publication a number of years back that the doping that goes into a semiconductor, the chemicals that they put in there, never actually stop doping the wafer or doping the die. During its lifetime, it's changing constantly. It's an incredibly slow change, but a transistor built today, 40 years from now, won't have the same characteristics due to the change, the chemical reaction never actually stopping within the transistor. Heat accelerates any chemical reaction, so running something that hot has to shorten its lifespan appreciably. At any rate, we've stabilized at 100 milliamperes at 38 C, which is perfectly comfortable temperature. Now I'm going to bump this up. Let's bump it up to, let's say 500 milliamperes. Let's go for broke. And there we have 500 milliamperes. That's 3.1 volts across the junction. It's not quite 500. I guess I can sneak that up a little bit more. That went over a little bit. The heck with it. That's close enough to 500 milliamperes. So 0.5 times, 3. That's 1.5 watts. So 3 volts, because you can see the voltage for some reason dropping. And we can see the temperature slowly climbing. So I'm going to just pause the video and let it stabilize. We appear to have almost reached thermal equilibrium at about 96 C. Oh, it's starting to climb again. It doesn't take much in the way of air currents to drop it real quickly. Oh, you can see the big drop it just did by me waving my hand in front of it. It made a big jump real fast. Slight current of air. I'll blow on it ever so slightly. So that little copper strip appears to make a fairly decent heat sink. Now we're running at 500 milliamperes, which is far brighter than any normal human being's ever going to have to run that thing for illumination purposes or backlighting on a meter or piece of equipment or whatever you wanted to do with these things. I got a ton of these. When we closed up the business here in the United States, I could have come home with 20 pounds of these things, and I should have grabbed more. I should have grabbed a big box of these things, but I just brought a couple of pill vials home. I have 2 or 3 of these pill vials full of them. But yet 94, we're climbing back up to 95. It seems pretty stable at that point. Let's crank it down. And 95, by the way, is way too bloody hot to put your hand on. You cannot hang on to that. That'll give you a blister if you tried to hang on to it. Let's drop it down to a human level here. I'm going to try 250 or 3. Let's try 300 milliamperes. There we go. There's 300 milliamperes, and the temperature appears to be dropping pretty quick. And we didn't lose much in the way of illumination out of this thing. And it's dropping pretty fast, down to a temperature I'd be a lot happier with it. I suppose if this was screwed down to a metallic surface, you could run it full bore. The fact that the pads are lifted up the diameter of that wire, you could put the metal copper down on the metal surface, and the LED will still be proud of the surface. So there'd be no danger of short circuit. And the temperature, of course, would be much, much lower. But now 78, those are temperatures I'm comfortable running semiconductors at. 75, 80 degrees C. So there you have it. The Rebel LEDs. Steve, they can be soldered. I'm just kidding. He managed to get them soldered. And I love busting his chops. But if he had used a decent soldering iron like in the opening credits, he'd have got the job done a lot quicker. Till next time, this is the Radio Mechanic. Thanks for stopping by. Oh, and please subscribe. Give us a thumbs up if you liked it. Even if you didn't give us a thumbs up, just let me know someone out there is looking. And subscriptions are great. Talk to you later. Bye. One quick last thing, and we'll wrap this up. I want to get this video on, and I don't want it to be any longer. I had theorized that we could bolt this thing down to a metal plate or chassis or something and sink the heat away a lot faster. You could add more LEDs. I ran the current up to 700 milliamperes, and right now it's stabilized at 122 degrees centigrade, which is pretty damn hot. You put your hand above it by about 2 inches, you can feel the heat coming off it. I'm going to just stick 2 alligator clips on the copper wire and watch what happens. The temperature is plummeting like crazy. That pretty much proves that this thing was bolted down to a metallic surface, which you could do with that little piece of copper, that these would absolutely run in the safe zone. You could probably put 3-4 of these on that one bar and run them at full current if it was completely bonded or screwed down to a flat surface. We're already down from 120, we're already down, we're approaching 80 degrees C. There's 87, 86. It's dropping like crazy. So if this was mounted on a piece of metal, it would really carry the heat away. That's it. Just thought I'd add this little piece to the end. Enjoy.